Hello everyone. Today we are going to discuss about the vehicle mechanics. The design of electric vehicle is a complex thing and it is mainly governed by the Newton's second law of motion, that is F is equal to m into E. And since this design of electric vehicle is going to include multidisciplinary branches, so it becomes very complicated. In such a situation, the method is to divide and conquer. So each entire design uh, process will be divided into various steps, and in each steps we are going to make certain assumptions as per the requirement, and also we are going to use some initial guesses and we will proceed with the design. Okay, so how the process is going to begin is, first we are going to consider one drive cycle, and from that drive cycle we will calculate the velocity at every instant. We will be knowing from the drive cycle, and from that we will calculate the acceleration, and from acceleration we are going to calculate the tractive force required, and from the tractive force we are going to calculate about the requirement of the motor, and from this data we will calculate or design the battery. This is how the procedure is going to happen. And before understanding about designing of the electric vehicles, we need to understand about vehicle mechanics, and for that we need to understand the roadway. Okay, so in this uh, today's class we are going to look into the uh, various aspects of the roadways. Okay, and also we are going to derive equation for gradability, uh, and also we are going to see the forces that are going to act on an electric vehicle. So if you consider a road will be given by 3 points. Okay, so I am going to have this kind of a road. This is road. Okay, so when I have this kind of a road, my vehicle will be there here, and this vehicle is going to move this kind of a, it is going to move in this fashion. Okay, and this is going to have this kind of a horizontal maneuvering, and this is going to have a up and down motion. Okay, so due to the um, grading in the road, it is going to have a up and down motion. And what I want to say here is, this vehicle is having three-dimensional motion. Okay, so it moves in x direction, it is going to move in this direction also, y direction, and also in this direction. Okay, but when we analyze a three-dimensional space, or whenever a vehicle moves in this kind of a motion, it becomes very difficult for analysis, and for that we are going to ignore this kind of a horizontal maneuvering. Okay, so here it is going to move in this kind of zigzag fashion whenever we are overtaking. So this kind of a motion we are going to achieve, and this kind of motion is ignored because it is going to have a less effect on tractive force required, and also the effect on motor required is less because of this kind of motion. So we are going to ignore that. So when we ignore that, we will have only two dimensions of motion. Okay, so either it is going to move in this direction, and whenever a slope comes, it is going to move up and down. Okay, so z is going to come into picture. Okay, so this is what we usually have with the roadway. But so we have two coordinates. What I want to say here is, this can be represented by a two coordinate system if we ignore this kind of a horizontal maneuvering. Now the same thing is expressed if you see the diagram. So the same thing is expressed by using x and y coordinates. Okay, so for simplification, there is a in textbooks it is given why we are going to consider this y and x coordinates here, and z we are not going to include because there will not be a motion in this direction. Okay, so it becomes a two-dimensional uh, plane. Okay, so now we are going to have a path. This is our path. Okay, so this becomes our path, and this is the x, and here I am going to have a vector in the x direction. Unit vector in this x direction is given by if. Similarly, I have a vector in the z direction or y direction, y direction, and it is given by j unit vector. Okay, so these two things I have. Let's consider the vehicle is at this point. Okay, let's consider that the vehicle is at this point. And now what is my intention here is I need to first calculate the position. Whenever you are measuring the distance, this becomes my initial position, and from this position it is moving. Now I need to calculate the position, or I need to determine the position, and from this position we will calculate the velocity. Okay, so now when a point is there here, how to represent this point? Okay, so there are methods in uh, 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 drawing. We are going to use something called as a Cartesian coordinate system. So the same thing we are going to use here also. So if you use the Cartesian coordinate system, it will be directly written as a this some 2 points we are going to represent, and this will be the point. This indicates the position. Another way is to represent it by a positional vector. Okay, so the positional vector is going to give us the position of any point in a plane. Okay, so this position vector is nothing but a line from this origin to that point. So that is nothing but the positional vector, which is going to represent the position of a point. Okay, so and here if I write this, I can write y of f. Y of f is a function of, it is a function of f of x. Okay, because as x is changing, the y is also going to change, and because of that what I say is y of f is nothing but a function of f x. Okay, so this is a about position vector, and this is the position vector which is represented by r vector, which is going to represent the position of any point. And now how this r vector is written? If you see the representation r vector, it is normally written r of x of s. Okay, so positional vector in terms of x of s is written as a x f x f I f cap if vector plus, similarly here it should be by xf j f. Okay, so what it is this point, whatever this point is there, this point is xf here. Okay, similarly, this point is yf, which is nothing but a f of x. Okay, so this term is going to come. For example, if you take here, I have some vector. Okay, so if this point is 3 and this point is 4, it is written as a 3i plus 4, 4i, this is written as a 4i plus 3j. The same thing is used here. Okay, so it is xf of if plus f of xf of jf. Okay, so this is going to happen between a, whenever this xf is between these 2 points. Okay, so there are 2 points here, a and b. Any of the 2 points you can consider a and b. In between this a and b, I am going to represent the position vector by this equation. Okay, now I have only the position, but there is a better way of representing a point, that is by using a tangent vector. Tangent vector. Okay, so what is this tangent vector? Tangent vector is going to give us the, for example, I have this point and there is another point like this. Okay, so there is another point here, so this is also another positional vector. Okay, so what is this tangent vector is, this is the vector, or this is the vector joining these two these two positional vectors. This is nothing but a tangent vector which will be tangential to this point. Okay, so this is called a tangential vector. Okay, so this is the tangential vector. And now how to write this tangential vector? So this is represented by t x of f. This will be equal to dr vector divided by dx of f. Why I have written here? So if you see this one, what is this vector? So this vector is going to represent nothing, this vector is nothing but how this dr is changing with respect to xf. So when I have at this position, so the r vector is this one. Okay, so as this xf is changing, or as this x coordinate is changing, the r itself is changing. Okay, so if I just take the derivative of these two things, so dr divided by dxf, that is going to give me this vector. Okay, so usually in normal Newton in mechanics, we are going to represent this by this kind of a thing. T we are going to write here, I'm going to write it as a distance. Okay, so this thing I am going to get. Okay, so whenever the position vector distance between 2 points is required, what I do is I will take the I am going to take the dr divided by dt. Okay, so we are going to understand it in a better way in the upcoming chapters. Okay, so this differentiation of d, or the rate of change of this dr divided is nothing but the txf. Okay, so this is given by, if I differentiate this equation here, this r vector is given. So if I differentiate this with respect to xf, I am going to get it as a if cap plus df divided by dx of j f. Okay, you can just check it. Okay, just I am differentiating this r vector with respect to dxf. So this becomes my tangential vector. And we have something called as a distance norm. Distance norm is going to give us the direct distance between these two uh, uh, positional vectors. So this is nothing but distance norm. Distance norm is given by, this is represented as a t x of f. Okay, is given by this equation. This is t x of f. This is nothing but square root of 1 plus df divided by dxf whole square. Okay, so this is coming from coordinate systems. Okay, so whenever I have this kind of a vector, and these 2 points, whenever I have a vector in the form of a plus jb, so it will be a 1 minute, I plus bj. Its norm is given by a square plus b square. Okay, square root of a square plus b square, the same thing is done here. Okay, just a minute. Okay, now I got the distance norm. Now I need to calculate the tangential, need to calculate the tangential shear roadway length. Okay, roadway length. So what you were seeing in this diagram, this tangential vector norm is going to give this direct distance, but actually there is a curve. Okay, so if I want to calculate the distance through this curve, I need to differentiate this norm with dxf. Okay, so then I am going to get the tangential roadway length. S is the tangential roadway length. Similarly, I need to express the percentage grade. This is given by this equation. So roadway, this one, right? Just a minute. Roadway percentage grade. This is nothing but a beta of x is given by tan inverse of differentiation of xf or y with respect to dx. Okay, so for example, in our analysis we have considered that there will be a grade in the uh, roadway. So I have this curve, there is a grade. Okay, so if I take the tan of this one, or slope, this will be represented as a delta y. Okay, so here similarly this is represented as a delta x. Okay, so this is going to give me the slope. Okay, so our grade. So this is the beta is the grade angle. Okay, so here we are going to consider the average at every point. This grade is going to vary, so we consider it as a average road percentage grade is given by this equation, that is equal to, that is nothing but a vertical rise divided by 100 horizontal distances. Okay, so horizontal distances, so this is called a percentage grade. So what is the meaning of this one is, for if I move 100 meters here, how much there is, how much difference I am going to get, or how much slope gets incremented, that is nothing but a average road percentage rate. In this equation, the units of this vertical rise as well as this denominator should be same. For example, here if you consider meter, here also it should be 100 meter. If you consider kilometer, here it should also be in kilometer. So that is the percentage, that is the average roadway percentage grade. Similarly, this is, and similarly this, the same thing is represented in percentage grade as delta y divided by 100 meter. So here this delta y is the vertical rise for 100 meters, and it is expressed as in percentage. It is nothing but a delta y percentage. Okay, so this is about uh, vertical grade, and in the next class we are going to discuss about laws of motion, and also on various forces that are going to act on an electric vehicle. Thank you.